Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step one aside as we jump into the Chapter 1 review in the Big Ideas Math Integrated Math 1 textbook. This is an actual portion of the textbook. It has 23 problems in total laid out from sections 1 to 5 in this chapter on solving linear equations. There are examples supporting each individual section to begin with in this layout. You can, by the way, download this in the description section down below, find the PDF according to this, and I'll lay out a timestamp for each individual problem as well as the beginning of each individual section. I think all you'll need at most maybe is a calculator, nothing to graph or anything like that. Get out some binder paper, download this, print this PDF if you'd like to. Otherwise, I'm going to go ahead and get started on it. So jump to the description section down below again to find anything that you like here. If you want to find individual sections within this where I made solution guide videos, you can find them in the playlist down below. Without further ado, I'm going to go ahead and get started. We are going to look at section 1.1 on solving simple equations. Solving simple equations for the most part is just a single step to solve, whether it's adding, subtracting, multiplying, or dividing to both sides of the equation. They say justify each step for these ones. Now they're writing justifications on the side, but they're also writing them in red. For me, that writing in red, not that I need to write in red, but what I write in red is my call to action for justification of each step. Whenever we have something like this one, x minus 5 equals negative 9, something that's affecting x, like 5 is being subtracted from x, we will use an inverse operation, like the addition property of equality, to get x by itself. If we have to subtract 5 to get negative 9, we'll add 5 to figure out what x's actual original value was. Negative 5 plus 5 is 0. X would equal negative 4 in this case. We could also double check that. Negative 4 minus 5 is indeed negative 9. That's a way of double checking. In the second example here, it says 4x equals 12. Justify each step. There's only one step to make, which is 4x means 4 times x. If we want to say a number times 4 is 12, we'll divide that number by 4 to figure out what it is. Now 4 divided by 4 is 1, so 1x is what we're looking for. 1 times x equals 3. The solution is x equals 3. So those are the two examples that you see. We're going to do these 3 problems within the section. The instructions are solve the equation, justify each step, check your solution. So on question number 1, z plus 3 equals negative 6. 3 is added to z and then we get negative 6. So if we subtract 3, then we can figure out what that original value was. Now 3 minus 3 is my action that I'm justifying to then get, therefore, z equals negative 9. I can double check that by substituting negative 9 back into the original equation. Check and see how negative 9 plus 3 compares to negative 6. Well, negative 9 plus 3 is negative 6, and this side is negative 6, and guess what? Those are equal, and that is my checking of my solution. Number 2, we have some decimal action going on. The variable is on the right side of the equation. It says 2.6 equals negative 0.2 times t. Now, the way that we generally would do this, and you might want to, some people would use a calculator in this play. I'm going to divide both sides by negative 0.2. As you saw in the example B, you divide by the number that's multiplying by your variable. Our number that's multiplying by this is negative 0.2, like this. Now here, if I divide both sides by negative 0.2, you can see 2.6 divided by negative 0.2, and your calculator would probably give you negative 13. When I say probably, I mean it should. So t equals negative 13. I can justify that by trying to see what 2.6 equals in comparison to negative 0.2 times negative 13. A negative times a negative is a positive. 13 times 2 is 26. Divide that by 10 if you know what's going on there, and you actually get 2.6 out. So that's all good. Now, there's another way that I can do this problem, but as I was actually looking at number 3, because I haven't done these problems yet, so I'm looking at number 3, I'm going to refrain from mentioning it until we finish number 3 and say how much number 2 and number 3 are actually alike. Number 3 says negative n divided by 5 equals negative 2. So it says negative n fifths equals negative 2. Okay, first things first. This is a division problem. Even though it looks like a fraction means division. Second of all, this fraction is negative, which the tricky part about that is that the negative is technically only assigned to one portion of the problem. Whether you're saying negative 1 is multiplying by the entire fraction, whether you're saying that the negative is on top, like negative n divided by 5, or whether it's n divided by negative 5. Either one or the other leads to a negative value, not, or you can multiply -1 by the whole set. It's not negative n over -5, for example. Not both of them are negative. Now, when I bring all this up, your best perception of this problem is to use it in this form here, because you want to get n by itself, so you want the other number to be the one that that has all the other stuff on it. Like you want the 5 to be negative, not n, so you can do something to the -5 to get it by itself. So when you do this problem as a kind of difference and rewrite, you can rewrite it as n divided by -5 equals -2. You don't have to write that, but it's just your understanding of what you have to do to get n by itself. N is dividing by -5. To counter that, use the inverse operation of multiplying both sides by -5. Now, -5 times n is -5n, but then it ends up dividing by the -5 below. -5 divided by -5 is +1. -2 times -5 is +10, and n equals 10. Now, I can double check that by substituting into the original equation. Just get rid of all that. Substitute into the original equation. Treat the fraction as the negative this time. Let's just call it -10/5, like that. And 10/5 is 2. Opposite of that is -2. So -2 equals -2, and that checks out. Now, Mr. Robinson, you said that this problem is a lot like number 2. It is. -n/5 is also -1n over 5, or -1/5 n. Dividing by 5 is also multiplying by 1/5. Why does that matter? Did you try 1/5 in your calculator by chance? If you do 1/5 in your calculator, or -1 divided by 5, you get -0.2. -0.2 is the value that's multiplying by t right here. So technically, this question could have also been written as -0.2n equals -2. So we could have divided both sides by -0.2, all that. And also on this problem, this could have been written as 2.6 equals -1/5 t, or -t/5. So if I wanted to solve this problem, I don't just have to divide both sides by -0.2. I could have also multiplied both sides by -5. And if you want to see what 2.6 times -5 is, 2.6 times -5, you also get that number -13. So they are related problems, and that's why I only technically did that one problem once. Anyway, I'm just exploring these values for you guys. Again, the whole idea of what I'm doing here is a solution guide video is not just giving you answers. I'm showing you workarounds of problems, the ways that you can identify what it is that you're doing exactly. Okay, keep all of that in mind when you're watching this. I want to make sure that you have a good, slow version of what's going on for each problem. All right, let's jump into section 1.2. Before we do hit problems 4 through 11, let's take a look at this example. 1.2 is on solving multi-step equations. Now, multi-step equation just so happens to be more than one step for different reasons. In this example they simplify the left side of this equation before they do any solving tactics like you saw in the one-step equation setup. They have -6x plus 23 plus 2x equals 15. -6x plus 2x are like terms and therefore can combine. You're not moving them to another side of the equation. They're on the same side currently right now. -6x plus 2x is -4x. Okay. -4x plus 23 equals 15. Left side is simplified, right side is simplified. Your goal to solve for x is now going to involve isolating your variable term. They subtract 23 from both sides of the equation. They didn't show it, but they wrote it. They subtract 23 from each side. Now, subtract 23 from 15, you get -8. So now -4x is all on its own. -4x equals -8. And then they show the next step. They're dividing each side by 4. And in dividing each side by 4, or -4, excuse me, -8 divided by -4 is +2. The answer is x equals 2. Now they're going to ask us to check our solutions. We can check their solution as well. -6 times 2 is -12. -12 plus 23, 23 minus 12 is 11. 11 plus 4, 2 times 2, equals 15. And that seems to pan out. So we're going to do the same thing. We're going to do it 6 times, and then they have numbers 10 and 11, where it's probably more of the same, solving multi-step equations, but in more of a geometric sense. So let's start with problem number 4. 3y plus 11 equals -16. We're going to subtract 11 from both sides of this equation, as, by the way, the left and right side are completely simplified. If we subtract 11 from both sides, that's one step down. We have 3y on this side and -27 on this side. Then I can divide both sides by 3 as 3 multiplies with y, and then we have y equals negative 9, excuse me. If we substitute negative 9 back into the original equation, we get 3 times negative 9 plus 11. Compare it to negative 16. This is negative 27 plus 11. And negative 27 plus 11 is negative 16. Negative 16 equals negative 16. We're all good. Okay. Number 5. 6 equals 1 minus b. Like I complained, sometimes the S's look like 5s. Sometimes I can make my B's look like 6s. So hopefully you note that's a 6, that's a B. Okay, we're going to solve for B. Now there's more than one way to go about this problem. One version of it is to get the B term by itself. We'll subtract 1 from both sides. But you got to be careful because that B is still negative. So when I get 6 minus 1 is 5, that's 5 equals negative B. 5 is the opposite of B, right? So we can switch signs around. That would mean that if I want to turn B positive, I'm going to turn 5 negative. Now that's not just a magic step, it also is a mathematical step. You could have divided both sides by negative 1, multiplied both sides by negative 1. Whatever you do to one side of the equation, you must do to the other side of the equation, and this is what we're doing right here. Negative 5 equals B, or B equals negative 5 is that answer. So do not forget a couple things here. Number 1, that B is still negative, and number 2, to address the fact that it's negative and turn it positive, consequently turn the other value negative. Just change their signs. Now the other way I can do the problem is this, and it's something that you're going to see me do in section 1.3 if the problems permit themselves to go that way. I can also add b to both sides. Now the thing about adding b to both sides is it moves it to the left side of the equation. Not that that matters in the grand scheme of things really, but it also turns it positive. So we get rid of that portion there. Now, how does the 6 interact with the b? 6 is a positive number separate from b, so now it says b plus 6 equals 1. And then I can subtract 6 from both sides like that, or you can do them all in one step, you know? You can do the minus 6 from both sides in one step like this, boom. That's what you'll sometimes see me do in the future here, not in 2 steps, or you can do it in separate steps like this if you want to organize your work that way. But you subtract 6 from both sides like that, and now you'll get b equals negative 5. So same answer, regardless of attempt. Let's go to the next little page here. Number 6. N plus 5n plus 7 equals 43. As we try and solve for n, remember that n as a whole means 1n. So that means this also means 1n. So when you see this n, this means 1n. 1n plus 5n is 6n. That's a simplification. Now that we've simplified the left side of the equation, this expression I should say, we can now solve for n using inverse operations. Subtract 7 from both sides because 7 was positive. Now we're going to get 6n equals 36. And if we divide both sides by 6, we get n equals 6. You know what? I didn't double check the previous question. Would you like to double check with me? The previous question, we got negative 5 as an answer, and 1 minus negative 5 is 1 plus 5. 1 plus 5 is 6. On the answer before that, we got y equals negative 9. 23 times negative 9 is negative 27, plus 11 equals negative 16. I suppose that's how I'm going to be double checking, if that's okay. We'll do it mentally. The original equation said n plus 5n. That's 6 plus 5 times 6, which is 30. Or 6 plus 30. 36 plus 7 equals 43. Okay. Number 7. We have negative 4 times 2z plus 6 minus 12 equals 4. There are multiple ways of solving this. Okay. Let me decide what to do here. Okay, we'll just leave this like this. We'll solve this 2 different ways, okay? First way I'm going to solve is probably more conventional than not. Simplify the left side of the equation. Negative 4 can distribute into these 2 terms here. That is a multiplication. We do negative 4 times 2z, which is negative 8z. Negative 4 times 6, which is negative 24. And then this minus 12 that was still hanging out says, hey, I'm still here. Don't forget about me. And that all equals 4. Now I can combine the negative 4 and negative 12. See, before I couldn't do 6 minus 12 because 6 was multiplied with negative 4. Now that 6 is turned into its proper value, it can combine with the negative 12 to become negative 36. So negative 8z minus 36 equals 4. Now that I've simplified this side, if you recall what I did on that previous problem where I got my variable term positive, you can do the same thing here, or you can add the 36 over for the sake of whatever, because I'm going to do this problem a different way as well. I'm going to go ahead and add 36 over to both sides this time, reminding you that when it comes to solving for this variable, you need to divide both sides by negative 8 and turn this answer, positive over negative, into a negative number. So z equals negative 5. So that's my answer. Now, we could double check by substituting into there, but I'm going to double check by doing it a different method, if that's okay. And maybe that's how I can justify how I got number 5 correct, was I did it 2 different ways. So let's do this a different way. Negative 4 times 2z plus 6 minus 12 equals 4. This will especially help when we do problem number 8, what I'm about to do right here. Instead of distributing negative 4 right now, I'm going to leave it as negative 4 times this. Keep in mind this is multiplication still, regardless. I'm going to add 12 to both sides, so I isolate not the variable, but I isolate the quantity that contains the variable. Now this will say negative 4 times the quantity 2z plus 6 equals, and this is 4 plus 12, which is 16. So here's the rewrite of that whole set. Now, remember, negative 4 is multiplying by this here, which distribution can be had. But if something's multiplying by something, that means that dividing by that value will eliminate that value from that side of the equation. If I divide both sides by negative 4, the negative 4 multiplying on top can also divide by the negative 4 on the bottom. See, treat this whole quantity like a single number. What if it was a whole x? Negative 4x equals 16. I could divide both sides by negative 4 then. I can do the same thing now. Divide this side by negative 4 and this side by negative 4. And the reason I'm looking to do that really, obviously to solve for z, but the reason why I saw it as a good option is because 16 can divide by 4. If it couldn't, I probably wouldn't like this option. I'd probably just go the other method of distribution. But now this is just 2z plus 6 on this side, and 16 divided by negative 4 is negative 4. So now I've cleaned this up in a way, right? I've made my number smaller instead of the bigger set of values that I had right here. That's something. And 2z is positive. So now let's subtract 6 from both sides. We have 2z equals negative 10. And then let's divide both sides by 2. And we get z equals negative 5. Now we had z equals negative 5 before. We have z equals negative 5 now. So that's my checking my solution. Did it a different way and got the same answer. I like it. Now, the reason why I bring that up is because number 8 could definitely benefit from using that method if you want to. It all depends. So on number 8, we have 3/2 times x minus 2 minus 5 equals 19. So we can do this 2 ways as well. We could either distribute the 3/2 into here. 3/2, by the way, is 1.5. That's another method. I'm not going to write 1.5. I'm going to keep it as the fraction. See how comfortable you are with fractions. 3/2 times x minus. Now, when you do 3/2 times 2, 3/2 times 2, the 2 here is multiplying with the 3 and dividing with the 2 here. I like to divide first. 2 over 2 is 1. 1 times 3 is 3. So this becomes a negative 3 like that. That's 3/2 times negative 2. If you use 1.5, 1.5 times negative 2 is negative 3. Then minus 5 equals 19. Negative 3 minus 5 combines to become negative 8. And we can add 8 to both sides of this equation to now attempt to get the variable term by itself. We get 3/2 x equals 27. And now 3/2 is multiplying by x, which means a lot of different things, and I'm not going to give every such perception. Remember, 1 is 1.5 x. You could divide both sides by 1.5. You could rewrite this as 3x over 2 if you wanted to, because x is multiplying by 3 and dividing by the 2, and do that in 2 steps. I'm going to treat it like the 3/2, but if I divide by 3/2, that also means multiplying by its reciprocal, which is 2/3. So I could say multiply both sides by 2/3 like this, and then that'll get me to properly calculate what's happening on the other side, where 27 is multiplying by the 2, yet dividing by the 3. Now 27 divided by 3 is 9, and 9 times 2 is 18. So 2/3 of 27, 27 times 2/3 is 18, and that's the answer for x. An alternative way to do this problem is the same thing that you saw before. You have 3/2 times x minus 2 minus 5 equals 19. Let's make sure that was the problem. Yes, it was. Now, we can do what we did last time instead of distributing, because look, 3/2 multiplied by x was a fraction. What if 3/2 times that number was a fraction? And then you're dealing with too many fractions in one. Maybe you prefer to have no fractions whatsoever at the stage. So instead, let's add 5 to both sides to get the quantity by itself that 3/2 is multiplying by this with. And then you can multiply both sides by 2/3 at this stage. And now all fractions be gone, given that 24 times 2/3 is an integer, which it is. So now we'll have x minus 2 equals, see, 24 can divide by 3. You get 8, and 8 times 2 is 16. And then we can add 2 to both sides, and you get x equals, once again, 18. So double checking by doing the method a different way, or by doing the problem a different method, it seems to still work out. So it depends on how you want to deal with those quantities, especially if they leave you with no fractions on the other side. That's a good method to choose. So it all depends on what you got. Of course, you can also turn 3/2 into 1.5. Not every fraction can turn into a good decimal, though. That's why I'm going to choose to refrain as often as possible. Some cases I will use it. Some cases the problem's already a decimal. We'll deal with it. Number 9 is already a fraction. Let's deal with this in this way. 1/5 w plus 7/5 w minus 4. And that'll equal 6. As far as combining like terms go, these two can combine. 1/5 plus 7/5 is 8/5. And they both have, so it's not just common denominator, they both have a w. So 8/5 w minus 4. So I've simplified the right side of my equation. Now I can do what we did previously, which is isolating the term with this fraction coefficient. We get 10 on this side, and 8/5 is still on that side. We can divide both sides by 8/5, or 8/5 is also 1.6. You can divide by 1.6. Dividing by 8/5 is the same as multiplying by its reciprocal, which is 5/8. So we're going to multiply 5/8 on both sides of this equation like so. 5 divided by 5 is 1, 8 divided by 8 is 1. Now on this side we have, take a look, w equals 5 times 10 all over 8. Now, as 5/8 times 10, I'm not done yet, but as 5/8 times 10 is not a whole number, 10 can't divide evenly into 8. 10 over 8 can reduce to 5 over 4 as a fraction that you divide both by 2. 5 multiplies with 5 here to get 25, and then it divides by 4. So you can write w equals 25 over 4. That is an accepted answer. As a decimal, this would be exactly 6.25. So this is also technically an accepted answer. Not every fraction has an exact decimal, so that's something I try and avoid whenever it's not exact. But because that one was exact, we could go for it. Numbers 10 and 11, they ask to find the value of x, then find the angle measures of the polygon. So on number 10, we have this diagram that says 110 degrees, 5x degrees, and 2x degrees, the interior angles of a triangle, and they tell you that the sum of the measures is 180 degrees. So I'm going to create an equation that says when I add 110, 5x, and 2x, I get 180. We're going to use that to solve for x. It's kind of a geometry equation, but wrapped up in algebra. 5x plus 2x is 7x. And now we'll solve by getting the variable term by itself. And then after that, getting the variable by itself. So this is 7x equals 70. And if you divide both sides by 7, you get x equals 10. Now that's solving for x, but that's not the full instruction of the problem. They also ask you to find the angle measures of the polygon. Now one of the angle measures is 110 degrees. They already tell you that. A next one is 5 times x. So 5 times 10 degrees, and I got 50 degrees. And the last one is 2 times 10 degrees, which is 20 degrees. You can double check all these by adding these together and see if they add to 180 degrees. They do. So that seems to pan out as far as the angle measures go. So solving for the variable and finding the angle measures. By the way, I totally slacked off on double checking my solutions from the previous set. I think I got a little sick of it over the course of the chapter. At some point I said, you know what, we're going to stop doing it. You notice I didn't substitute 25/4 into that one. I'm not double checking anything. Well, I did double check. I saw that all these added to 180, and they do. Okay, number 11. Number 11 is a pentagon. Doesn't quite look like a home plate, so I'm not anticipating any 90-degree angle answers. But the sum of the measures of this pentagon, five-sided shape, is 540 degrees. So when I add these angles, I got an X here and here. So check this out. I got an X here and here. That means I have two X's. Two X's, literally. 2X means 2 times X. Plus, and then I have 3 X minus 30s. 1, 2, and 3. I have 3 of those. Wrap it around parentheses. They already have it in parentheses, but they have that to represent degrees. They really have it to represent that it's a single quantity. And that's the thing. We got to triple the quantity. So 2x plus 3 times x minus 30, and this all equals 540. We solve by what we've done before. Now this time, I don't want to try and get this by itself and divide by 3 or whatever, because this is a 2x. 2x won't combine with 540 by subtracting it over. The only way I want to solve this problem is through distribution of the 3 and then carry on from there. So 3 times x, 3 times negative 30 gives us those values. Now we can simplify doing 2x plus 3x. And now I can add 90 to both sides. That is 630. And then we divide both sides by 5. 630 divided by 5 is 600 divided by 5 is 120, an extra 36, so 126. X equals 126. Now, there are 5 sides to this diagram. I'm going to kind of draw it out this time. And therefore, 5 angles to this diagram. There are 2 of them that are literally x degrees. That means this is 126 degrees, 126 degrees. The others are 126 minus 30. 126 minus 30 is 96. So these are each 96 degrees, 96 degrees, and 96 degrees. This, by the way, is totally not drawn to scale, but this is the diagram here. Please make sure you're leaving the degree symbols anytime that they are asking for measures of angles. Okay. All right, let's move forward to section 1.3, solving equations with variables on both sides. Now, 1.1, 1.2, and 1.3, I think, are complete build-offs of one another, which means what you're graduating from one to the next. This is the next step forward in solving algebraically. What if you have variables on both sides? Simplification still might be had. Isolating your variable terms one thing, but first you got to collect your variables on one side of the equation. So what they do to begin with on this problem, in this example, is they distribute the 2 and the negative 4. Totally fine. We'll work it out. Now, there are y's on both sides of the equation. 2y here, negative 4y here. Suddenly, 2y turns into 6y. How come? Well, same reason as the negative 4y went away. They added 4y to both sides. Negative 4y plus 4y is 0 and added it over here. Could have we subtracted 2y to the right side of the equation? Yes. Is that preferred? No, for 2 reasons. Number 1, the less important one, it moves it to the right side of the equation instead of the left. That really doesn't matter in the grand scheme of things, but sometimes people like seeing things on the left side instead of the right, so there's that. Now, I'm going to move things to the right side of the equation at the cost of, the second reason, number 2, my variable term is positive. I much prefer my variable terms being positive instead of negative. You've already seen me do that from a problem before, at least as an alternative method. On these problems, I'm always going to err to the side of making them positive. Now, there are special cases in this section of problems where sometimes your variables will cancel out, and we'll talk about what happens in those situations. So, anyway, they add 4y to both sides to get 6y. Now they're going to add 8 to this side, both sides of the equation, I should say, to get the variable term by itself, and then they divide both sides by 6. Divide by 6 to get the variable by itself. They're not asking us to double check these, so I gladly won't. But on number 12, let's go ahead and initiate the setup. 3n minus 3 equals 4n plus 1. This is a case where, again, getting your variables on one side of the equation can either get you to subtract 4n from both sides, that would move it to the left, but notice 3 minus 4 is a negative number. You know what I'd rather do is I'd rather subtract 3n from both sides, which, although it moves it to the right side of the equation, it makes this a positive number. In fact, this leads us right near our answer. And if I'm moving the n's to the right side of the equation, I should move the constants to the left side of the equation. I'm going to do them in one step. I'm going to subtract 1 from both sides like this. 1 minus 1 is 0, so we have that movement. Negative 3 minus 1 is negative 4. 4n minus 3n is 1n. Negative 4 equals n, that's n equals negative 4. We're done. Technically, 2 actions were done, but I kind of did it in one step. I feel good about it. That looks good. Okay, number 13. We have 5 times 1 plus x, the quantity, equals 5x plus 5. 5 times. Okay. I'd like to distribute first. So I get 5 plus 5x equals 5x plus 5. I don't know if that looks a little weird to you, or if you, hopefully you know what's going on. It's like Blue's Clues. You're like, you got to do the thing. You got to... So in a case like this, look, we're trying to get x's on one side of the equation. If you notice, the 5x's are the same. So like, what do? I guess you can subtract 5x from both sides. What would it do? Well, 5x minus 5x is 0 here. 5x minus 5x is 0 here. You're left with 5 plus 0 equals 0 plus 5. Ultimately, the x's become irrelevant in the grand scheme of things of this problem. Could I also subtract 5 from both sides? Sure. But then you get 0 equals 0, which is just another truth statement, just like 5 equals 5. What's happening here is the left side equals the right side. Left side equals the right side. This is what's called an identity. From the beginning, this equation was an identity to begin with. Left side was the same as the right side. They were both one the same. This doesn't mean x equals 5. This actually means x can equal anything. It means no matter what I had for x, they didn't end up affecting the overall truth of the problem, which is that the left side will always equal the right side. 5 equals 5 is true. Now, that's not our answer either. Our answer is technically all real numbers, which is an infinitely many solutions case. Identity equations such as this one will result in or conclude in infinitely many solutions. Number 14, we have 3 times the quantity n plus 4 equals 1/2 times 6n plus 4 as a quantity. Let's distribute the 3 and the 1/2. Remember, multiplying by 1/2 is the same as dividing by 2, which is nice for these two even numbers. 3 times n, 3 times 4. 1/2 times 6. 6n divided by 2 is 3n. 4 divided by 2 is 2. We have 3n plus 12 equals 3n plus 2. Number 14 is kind of like number 15, or no, I don't know what number 15 is like. It's kind of like number 13 in that you have the same variable term, same coefficient on both sides. By subtracting 3n from both sides, it'll go away. I'll start with that. But let's look at this logically first and ask ourselves what the heck's going on. 3n plus 12 equals 3n plus 2. There's no typo here. Everything that I wrote was correct. But how will that work? Some number plus 12 equals the same number plus 2? What number can I substitute for n to make that true? Well, I don't know. So let's explore further. Let's subtract 3n from both sides. And whether I do anything with the constants or not right now, this equation is going to say 12 equals 2. Again, I didn't do any mistake. I didn't make any mistake in my math. There's nothing wrong there. But 12 equals 2 is not a true statement. That lends to state that no matter what I substitute for n, I'm never going to be able to make the left side equal the right side. 3n plus 12, again, some number plus 12 equals some number, the same number plus 2? I don't think that's really possible. So my conclusion I need to make, and you do need to make one, is that there's no solution here. Remember, when it comes to solving for a variable, we like to generally express the one solution that it is. The one solution is n equals this, x equals this, q equals this, even if it's 0 or a fraction. But in the previous case, it was substitute whatever you want. It's always going to work. In this case, it's substitute whatever you want. It's never going to work. And that's the case of number 14. So 13 and 14 were special cases, like I warned of previously. In non-special cases, I try and get my variable term positive where I can. Okay, let's move to section 1.4. We are solving absolute value equations in section 1.4. Absolute value is a way of saying distance from 0. When you take the absolute value of something, sure, it turns positive once you represent the entire quantity. That being said, beforehand, you have to ask yourself, again, what you're taking the absolute value of to get your number. In absolute value of x minus 5 equals 3, we're asking, what can I take the absolute value of to get 3? The numbers are either 3 or negative 3. So we're introspectively looking inside the absolute value symbols there, inside the function, and saying, this x minus 5 number, not x, but the x minus 5 value could have either been 3 or negative 3. We create two different equations for that to solve for what x could have been as a whole. If I add 5 to both sides of this equation, I'll get x equals 8. If I add 5 to both sides of this equation, negative 3 plus 5 is 2. X equals 2. The solutions are x equals 8 and x equals 2. We can double check that. 8 minus 5 is 3. Absolute value of 3 is 3. 2 minus 5 is negative 3. Absolute value of negative 3 is 3. So absolute value equations can have more than one solution. And I don't just mean the infinitely many solutions thing. I mean, it can have two solutions in those cases. It can have one or the other because plugging in one number ultimately gets you the positive version of the number you take the absolute value of, and plugging in another number can get you the negative version of the absolute value. So that's one example. The second example, part B, example B, says absolute value of 2x plus 6 equals 4x. Now we can set up the same scenario as we did last time. This has an x on this side, which is going to change something in a bit. But we're setting up the same thing as last time. This 2x plus 6 can either equal positive 4x or negative 4x. When we solve for x, they subtract 2x from both sides. I like that. It keeps your x's positive. And then divide both sides by 2, you get x equals 3. Now in this case, they subtracted 2x from both sides. I don't like that as much. It turned them negative. I would have rather added 4x to both sides, but that's okay. When they subtract 2x from both sides to make this negative, they then divide both sides by negative 6. Don't forget that. They get x equals negative 1. Now when you double check these, take a look at their double check on this. Plugging in 3 into this is just fine. You get 12 equals 12. Remember, there's an x on this side as well where 3 needs to substitute, and that's a positive number. When you take the absolute value of something, it will turn positive. So that's the only way that this will work out if the right side is positive. But if x is negative 1 and you substitute that into here, the issue isn't the left side. Well, it sort of is because the left side is not going to match the right side. The issue is we're going to take the absolute value of something, and the right side is negative. 4 times negative 1. You can't take the absolute value of any number and get a negative as a result. The smallest number you can actually get is 0. Otherwise, they're all positive. So 4 does not equal negative 4. That doesn't work out. X equals negative 1 appears to be an extraneous solution. The only solution is x equals 3. We reject x equals negative 1. I don't actually physically say that in any sense, but we reject that answer. It doesn't work. So there are some answers that can be introduced that do not work, that will, for our sake, that will only appear in problems where you have a variable on the other side of the equation, or it's represented on the other side. See, you have to get the absolute value portion by itself. When you get it by itself, on the other side of the equation, if there are variables, they could mess up things because you might take the absolute value of a number that turns it positive, and this becomes the negative version of that answer. Now, just to say it straight up, when I look at numbers 15, 16, and 17, I see no such concerns for those to get extraneous solutions. I will double check on number 17, but 15 and 16, I have no reason to need to double check. When the other side is strictly a constant, we're all going to be good. This side has a variable on it, but it's also wrapped in an absolute value, which gives me all hope that it's going to give me true answers for any two answers that I could potentially get. That being said, let's move on to the setups. Let's go to number 15. We have the absolute value of y plus 3 equals 17. This is a case, once again, where we try and see what can y plus 3 become. It can be 17 or negative 17. Either or, you take the absolute value of either of those, you will get 17 as a result. Now, what value of y can we get? We subtract 3 from both sides to figure it out, whether it's this problem or that problem. Now, 17 minus 3 is 14. Negative 17 minus 3 is not negative 14, but rather negative 20. So y equals 14 and negative 20. Double check for yourself. Those should be able to work out. Number 16. Number 16, we have negative 2 times 5w, absolute value 5w minus 7 plus 9 equals negative 7. We subtract 9 from both sides here to isolate the absolute value. That's our first stage. Negative 2 times, again, 5w minus 7 in absolute value. This equals negative 16. Now, I can't distribute negative 2 in here because the absolute value protects it. However, I can divide both sides by negative 2 like we saw in those previous sets of problems with parentheses around it. And negative 16 does divide by negative 2, which is a good thing for us. But you have to do it regardless. We're going to have to do that regardless. Now, absolute value of 5w minus 7 equals positive 8. Now, previously, this showed a negative 16. If this was absolute value of 5w minus 7 is negative 16, there would be no solution because you can't take the absolute value of something and get a negative out as a result. That being said, it's now positive once you divide it by the negative and the absolute value is by itself. So we can set up as we did before. Either 5w minus 7 equals positive 8 or 5w minus 7 equals negative 8. Now, the same thing's going to happen in both equations where we will add 7 to both sides, and then we will be dividing both sides by 5. The difference is 8 plus 7 and negative 8 plus 7 give you two different answers. So when we divide by 5, we'll also get a different appearance in that portion as well. So here 5w equals 15, whereas here 5w equals negative 1. When I divide both sides by 5, lucky me, this divides out evenly. You get w equals 3. And over here, you get w equals negative 1/5. I'm just going to leave it like that. There's also negative 0.2. We actually literally saw that number, negative 0.2, before when you divided. So you could write that answer as well. And that should be good. We should be good on that. Now, number 17, we have absolute value of x minus 2 equals absolute value of 4 plus x. You know what? Never mind. Let's do the problem. Okay, so in this situation here, remember, they have absolute values on both sides. This one's by itself, which is a good way of still doing the setup. It doesn't matter whether this has absolute value wrapped around it or not, other than in your double check. We still got to see whether the inside thing can either equal the positive or negative version of it. Because here's the thing, if it's the negative version of that answer, absolute value of a negative is still a positive, so it should still work out that way. So either x minus 2 can equal positive 4 plus x, or x minus 2 can equal the opposite of 4 plus x. Remember, 4 plus x is an entire quantity, so we're talking about negative 4 plus x like that. Now, in a problem like this one here, let's just do the left side first. In a problem like this one, notice that there are x's on both sides of the equation. If I subtract x from both sides, this is the same issue that we've had on previous problems where the x's cancel, right? We have negative 2 equals 4, which is not a true statement, which means there's no solution for that situation in x. So what I was going to say, when I said, you know what, I was going to say, you know what, it's not that you're always going to get two answers, because you could also get a special case like this one, but it's not that there was an answer to try and plug in. Nothing's extraneous here. There's just no solution there. Do I write no solution? You got to wait, because there's a potential for a solution over here. If neither works, we'll say no solution in full. But in this one, let's take a look. We get x minus 2 equals, and if I distribute the negative, this becomes negative 4 minus x. And now, in solving for x, I'm going to add x to both sides. And keep in mind, guys, x means 1x. So negative 1 plus 1 is 0. 1 plus 1 here is 2. This is 2x. Now, I can also, at the same time, add 2 to both sides. Negative 2 plus 2 is 0, and negative 4 plus 2 is negative 2. So you divide both sides by 2, and you get x equals negative 1. Now, you can double check for yourself. I'm going to be fully convinced that that is an answer and the answer for the problem. There's nothing wrong with it. The only check for extraneous solutions for me, once again, will be when x is outside of an absolute value on the other side of the equation to solve, because that's where potential for lending to a negative version of an answer can come into play. Will it always? No, it won't always happen. You don't have to have extraneous solutions. And listen, sometimes you can have two extraneous solutions, both of them, in which case that would also be a no solution answer. All right, number 18 says the minimum sustained wind of a Category 1 hurricane is 74 miles per hour, minimum. The maximum sustained wind is 95 miles per hour. We're going from 74 all the way to 95. Write an absolute value equation that represents the minimum and maximum speeds. Okay, so what I want to do here is represent this one on a number line, kind of graph it, if you will. They didn't ask us to graph the other ones, right? They did not. Okay, so imagine on a number line that you have, all the numbers in the world, and right here you have 74, the minimum speed, and 95, the maximum speed. We can sway our answer all the way from 74 to 95 and everything in between. Now there's a middle value for which we can add and subtract equal amounts to become the minimum and the maximum here. I'd like to find out what that minimum or what that middle value is between the minimum and the maximum. How much are we adding or subtracting in between? There are two ways to do this. You can either find half the distance of 74 and 95 and then add that distance here, add that distance there. Or you can find the average of those two numbers and get it. I'm going to do the half the distance one just because the numbers are already kind of big. 95 minus 74 is 21. And we'll take half of 21. This time I'll write it as a decimal, 10.5, 10.5. Half that distance is the middle value of 74 plus 10.5 or 95 minus 10.5. Whichever way you go, you should get 84.5. Now, 84.5 matters here because the difference between any number in your set and 84.5 has to be within 10.5 units of either direction of that number, which leads to 74 and 95. So if I say x minus 84.5, that is the difference between x and 84.5. But I want my difference to be 10.5 in either direction, left or right, positive or negative. That's why we say absolute value of x minus 84.5 equals 10.5. If I solved this equation, it would get me, now x represents the speed of the wind as a variable. I want my speed of the wind to either be this or that to represent the min or max. The difference between 95 and 84.5 is 10.5. The difference between 74 and 84.5 is also 10.5. It's negative, but if I take its absolute value, it turns positive. And that's why we do absolute value here. So if you solve that equation, these are the two answers we'd get. X equals 74, x equals 95. Okay, last section is 1.5 on rewriting equations and formulas. We have two examples to go off of. This is where we have what are called literal equations. This is where when you solve for your answer, besides the no solution and things like that, your answers aren't just going to be a number. They're going to have other variables in it. In this part A, or example A, they talk about, ooh, this is good. We're going to do this in chapters 3 and 4. The slope-intercept form of a linear equation is y equals mx plus b. Now, normally you want to get into this form. They're going to get you out of this form by, say, solve for m. Notice they put m in blue, so we can follow along m until we get to the answer. Solving for m means get m by itself the same way you would any other variable. Now, you got to treat x like any other number. X is multiplying by m, so eventually we're going to divide by x, but not till the very end. First thing we're going to do is subtract b from both sides. b minus b is 0. Now you got this term by itself. Y minus b does not combine. They stay as y minus b here, so they simplified that. Now, you divide both sides by x, because x is multiplying with m, and that means every term on this side also divides by x. Whether you divide them individually or collectively, this whole set is dividing by x, and that's your answer. M equals y minus b all over x. Now, m in these equations represents slope. Not that we're talking about that stuff right now, but that's so you can also find the slope given some y and x point that you have and the y-intercept of your equation. But m equals that, so if we substituted values for y, b, and x, we could find out what m was. Now on part B, we have another equation. This one is also an actual formula, finding the surface area of a cylinder. They say solve for h in the formula. H is once again in blue. So in this situation, you want to get the h term by itself by subtracting anything that's positive and adding with it as a separate term. So they subtract 2 pi r squared in a way that s minus 2 pi r squared, once again, do not combine. And then you divide by everything that's multiplying by h. Divide both sides by 2 pi r. Remember, that means 2 times pi times r, but they're all in the denominator together. Now, we did this exact example previously in section 1.5, I believe, whether it was in the example set or in the problem set. But h equals s minus 2 pi r squared over 2 pi r. I know you might be compelled to say, let's cancel, let's cancel, let's cancel. At the time of section 1.5, I also mentioned why you cannot do that, but I did show another way that you could rewrite it if you split up the denominator into two different terms with that fraction. S over 2 pi r minus 2 pi r squared over 2 pi r. Those ones can lead to some division on the second fraction, but we're going to leave them collectively as a whole right there. All right, let's do our final five problems here, starting with number 19. Solve the literal equation for y. In 19, 20, and 21, we are solving for y. So 2x minus 4y equals 20. Now, in the first two problems especially, I'm going to get in the habit of what we actually want to do from an equation like this to an equation in solving for y. I actually want to make it look like this form personally. It has to do with what we're going to be doing later with them in future chapters. I believe chapter 4 when we do rewrites. of these equations. So I want to make it look like y equals mx plus b as well, okay? That means I'm going to subtract 2x from both sides, but when I do, keep in mind on this right side of the equation that 20 minus 2x do not combine, but I'm actually going to write the x term first. Negative 2x and 20 is positive. Is that a requirement? No. Do I prefer it that way? Yeah, it's a visual that I do for myself to make it look like, again, this form. X term is first, the constant term is second. This is just a personal preference. Now, on this side, 4y is still negative. Don't forget the fact that 4y was negative to begin with. It stays negative until you do something about it. When I divide both sides by negative 4, that is me doing something about it. Now, in cases with numbers, there's oftentimes you can do true division or fraction reduction. In this case, you can do both. Y equals negative 2, x is dividing by negative 4, and 20 is dividing by negative 4. Negative 2 divided by negative 4 reduces to positive 1 over 2. We can write that as 1/2 times x. And as far as slope-intercept form goes, this is the preferred way you'd want to write it. Not x over 2, not 0.5 times x, but 1/2 x, literally like that. 20 divided by negative 4 is actually negative 5, so adding negative 5 becomes minus 5. So this is my preferred version of the answer, y equals 1/2 x minus 5. There's also, negative 5 plus 0.5x, things like this. But as far as when we graph these later, you're going to want it to look like that. Number 20, more of the same. We have 8x minus 3 equals 5 plus 4y. We are solving for y. It's not quite the standard form that you saw previously, but it doesn't change the fact that we're still getting y by itself. Y is on the right side of the equation. Oh well. I'm going to keep it on the right side of the equation as long as it's positive. When I get to my final answer, I'll write it on the left side of the equation. So I'm going to begin by subtracting 5 from both sides, like so. Get the y term alone. We have 8x minus 8. That's negative 3 minus 5. And then we divide both sides by 4 here. Maybe this problem is arguably easier than the previous one. Remember, both terms divide by 4, and guess what? Both terms can divide by 4. So I'm going to do that. Now, over here, I'm going to write y equals, write it on the left. Write it on the left. And on the left side, or now to the right side, I'm going to write 8x over 4, which is 2x, negative 8 over 4, which is negative 2. So y equals 2x minus 2. In our final example of this set, this one gets a little bit different, number 21, because we have significantly more letters involved. Not just, by the way, literal equations are equations with more than one variable. Last time we had both y and x. This time we have 3 variables. We're solving for y still. The problem with this one is we have 2 different terms with y, and neither term combines with each other. Not in the way that you'd want, not that they mesh into a single number. 9y plus 3yx is not 12y x or 12y or anything like that. They don't combine the way you want them to. But what you can do is represent them as an addition of the 2 coefficients. In fact, I'm going to rewrite this as 3xy. Not only will it help me with the problem, but also I prefer alphabetical anyway, 3xy. So this might help you with the problem as well, because 9 is the coefficient here, and you can treat 3x as the coefficient here. If I add 9 and 3x, again, they don't combine to a number, but they infuse together to represent the 2 terms that add from y, such a way that y is multiplying by the quantity 9 plus 3x. Now, if you're confused on that stage, remember, I did do these in section 1.5. You can hear more about it. The word that they use is distribute, which is technically opposite of what we're really doing, because this is where I would distribute y times 9 to get this and y times 3x to get that. But we went backwards. We kind of did anti-distribution. There's a word for it. It's called factoring. So if I ever say the word factoring in the video, that's what I'm referring to. Let me move these up a little bit. Now, we're going to learn more factoring in IM2, but you're getting a good dosage of it right here. Why did I do this? Because I got a single y in my equation now, and I want to solve for y. And whatever's multiplying by y, we've seen this before. When 4 multiplies by y, we divide by 4. When negative 4 multiplies by y, we divide by negative 4. When blah, 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 blah. Here, 9 plus 3x is multiplying by y. So what can we do? Divide both sides by 9 plus 3x. Remember, it represents a single term, even if it's not written as a single value. Anything divided by itself, 9 plus 3x over 9 plus 3x is 1, provided that it's multiplying by your factor. So y equals a divided by 9 plus 3x. Nothing I can really reduce there. I'm going to leave it like that. That's my final result. Okay, 2 more questions. Number 22, the volume V of a pyramid is given by the formula V equals 1/3 area of base times height. True. Where b is the area of the base and h is the height. Solve the formula for height. So we need to get h by itself. Let's solve for h. So in terms of solving for h, I'm going to do this one at a time. First, I'm going to multiply both sides by 3. Keep in mind, 1/3 times something means dividing that by 3. So if I multiply by 3, I've busted that fraction. We now have 3 times v equals b times h. And I need to solve for h. And keep in mind, I just said b is multiplying with h. So I can divide both sides by b, and we will get h equals 3v over b. 3-volt battery. I don't know. 3v over b. The height, you can triple the volume and divide by the base area, and you get volume. It says find the height of the pyramid. Now in this pyramid, we have, that was part A, by the way. For part B, find the height of the pyramid. They say the volume's 216 cubic centimeters. The base is 36 square centimeters. So I can use the formula h equals, I can do 3 times this 216, and I can divide this by this 36. Now, in terms of helping myself out with the problem a little bit, I know 216 divided by 36 is 6. That's just a personal thing that I know. And 3 times 6 would give you 18. Now, the height also has units. It's going to be centimeters. It is a one-dimensional unit, so it has one-dimensional length there. That's number 22. Okay, about a few minutes before we hit the hour mark here, let's do number 23, see if we can beat it. It says the formula F equals 9/5 times, now I'm not going to speed up to beat it. I've actually been intentionally, if you've noticed, because normally in my videos I go pretty fast, guys. If you notice, I've been going very slowly on this one, even in my speech. I'm not going to go that slow on the practice test that I do in cumulative assessment, or the chapter test in cumulative assessment. Because that's going to be, as I generally say, less teaching, more doing. This one I'm trying to teach the whole thing as a lump sum. Anyway, this is converting Kelvin, degrees Kelvin to degrees Fahrenheit, or Kelvin to degrees Fahrenheit. It says solve the formula for K. K is all within this, wrapped around this set right here. The first thing that I'm looking at is this 32 that's added to the whole thing. We got to subtract 32 from both sides to begin with here. Now, this becomes F minus 32 on the left. And on the right, I still have this 9/5, which of course is the next thing kind of to take care of. So this is times K minus 273.15. Now, if I multiply both sides by 5/9, again, you've seen this before. Now you can see why distribution might not be the matter that we want to try and do. Instead, we want to do this. Remember, 5/9 is multiplying by this quantity, not by just F, right? You don't just get to pick and choose which one. Oh, we multiply by the first one. No, you multiply by the whole thing. F minus 32, whatever F is, needs to combine and become something first, order of operations. Over here, you still have K minus 273.15. And then we add 273.15 to both sides because it was subtracted over there. Now, this doesn't combine with anything over here, not even with the negative 32. That's wrapped around parentheses, so it'll be its own thing. So we'll say K equals 5/9 times the quantity F minus 32, and then plus 273.15. We can go from degrees Fahrenheit to degrees Kelvin. It may look complicated, but that's the barest of ways of which we should probably attempt it. That's part A. It says part B, it says convert 180 degrees Fahrenheit to Kelvin. K, round your answer to the nearest hundredth. When they say round your answer to the nearest hundredth, it sounds like we're going to have to use our calculator, and it's going to be a longer winded decimal, maybe a repeating decimal from there. So we'll do 180 minus 32, and then plus 273.15. Now, the most I'm going to do before I let the calculator take over is I'm going to do 180 minus 32 right now, which is 148. As 148 cannot divide by 9, I'm going to let the calculator, like I said, take over. Not do any early rounding. Let's go straight to there and figure out what we got. We got 5/9, which in itself is a repeated decimal. Look at that. Boom. We got 5/9 times 148 minus or plus 273.15. And my answer here is around 355 point, they say nearest hundredth, that's 2 decimal places, 355.37 Kelvin. So K is about 355.37 Kelvin. K is actually literally the unit for Kelvin, which is kind of weird to see. K equals this K. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Hopefully this vested you in the chapter a little bit more. So cool there. We're going to do a chapter test and cumulative assessment where I'll go blisteringly fast in comparison of problem by pace. So thank you guys so much. Take care. I will see you in that next one.